Mhm. Mm. Okay, good morning, everyone. So I would like to start today's lecture by just taking a bit of an overview of what we have achieved so far. So we started, okay, giving this historical introduction, motivating a little bit why there is a connection between statistical physics and computer science. And then we practically started studying this model, the curve-wise model, which was introduced as a model for the ferromagnetic and paramagnetic phase transition. And then we went on to derive a large deviation principle for this model, which essentially was telling us that, if you look at this high dimensional a priori complicated probability distribution, actually it's a very simple probability distribution in these guys when the dimension is high. So exactly in the regime where apparently it's hard to do things because sampling is hard in a high dimensional probability distribution, it actually simplifies. And for that particular model, and here I stress again that this is something that it's exact for that particular model, but in general might be more complicated. We saw that actually the measure completely factorizes once you condition on the average magnetization. And moreover, the average magnetization concentrates to a value that can be determined by just solving like a one-dimensional equation for the rate function of this large deviation principle. So that's quite astonishing, right? Because this apparently very complicated problem to sample by just like running any sampling algorithm you like becomes very simple. You just like need to solve this one-dimensional problem, you get your magnetization, and then you just sample IID from some Bernoulli like with a certain probability determined by this magnetization. So that's quite nice. And then we went on to study like the phenomenology of this model, and this was an opportunity to learn a little bit about phase transitions in physics. So in particular, we saw two types of phase transitions. So the first phase transition was for zero magnetic field and was a continuous or second order phase transition, where we saw that, a point which was the only extremizer of this large deviation principle went from being a maximizer to being a minimizer continuously. And these type of transitions are nice because we can just study these transitions by studying like the Taylor development of the rate function because they are continuous. So you can determine exactly when the transition happened. Then we went on to study like the case of non-zero magnetic field, external field. And then we saw that for that case, things were a little bit more complicated because you can have like a first order phase transition. So that's a discontinuous phase transition characterized by the fact that if you look at this landscape or rate function for the average magnetization, there is a critical field below which you have a discontinuous like minima appearing. And this minima is not a global minima. So you have a global minima and you have a local minima. And this has very important consequences for algorithms because since I try to argue that since the energy barriers in this landscape are order 1 energy barriers, in the configuration space, this means that they are order D. And this means that to jump then you actually need to take exponential time in D to be able to go from one to the other. So in practice, if you have like, a finite time running something in your computer and you run, let's say, a sampling algorithm, actually you never mix. Like you actually just see one of the two minima, the one which, if you're running a, let's say, a descent algorithm that is just going down in energy, you're just gonna see the one closest to the initialization point. And that has some consequence for the hardness of sampling in this model. And actually, a very nice exercise that if we had more time, we could do is that I could ask you to actually implement, let's say, Glauber dynamics or Metropolis algorithm for this model, and you see very clearly like that, you don't mix. It's very easy exercise to do, and that's something usually we do in the course when I teach this course for a semester. Okay, so then we kind of closed this chapter, and then we started seeing, okay, I started arguing that, methods of the statistical physics that are used to analyze this type of very simple physical models for ferromagnetism can also be used to understand computer science problems. So I introduced two types of problems that we are going to be looking. One is like inverse and inference problems on one side, and the other are learning problems, so empirical risk minimization. So I just throw on the board a couple of problems. One way I could have given these lectures is that I could just give them these lectures about one of these problems. You know, I could just have said, let's study, let's say, ridge regression, and then go on and then draw a lot of conclusions about ridge regression. But the way I decided to do this instead is like to give you some kind of toolbox. So that's why I'm like scattering some problems, and we are going to be hopping in and off different problems, and trying to just like highlight some interesting phenomenology. But the focus is actually in the methodology. So that's why I wanted to show you that actually this technique can treat very different problems under the same umbrella. And so the whole idea is that, you know, I'm going to be talking about a very kind of generic or abstract setting, and then we can specialize and try to draw consequences for your favorite problem. You're interested in phase retrieval, so we can do phase retrieval. If you're interested in, you know, compressive sense, we can do compressive sensing. Okay, so that's where we stopped last time. I just put this list of 6 problems in the board. So I'm not going to write this again. Instead, like today, what I'm going to do is that I'm going to be focusing on how to derive a large deviation principle for this class of problems. So let me start by just introducing exactly the setting that we're going to be studying. So this is going to be the setting of generalized linear estimation. So we are basically going to assume that we have, like, you know, data. Data is going to come in pairs. So let's say xi, yi. And I'm going to have n data points. So this notation I use for the discrete set 1 to n. Okay. And I'm going to be assuming that x is going to be a vector in Rd, and y is going to be, you know, some set that can be either, like, you know, continuous if you're doing some kind of regression, or can be binary, or, you know, can be discrete if you're doing classification, for example. I'm going to be assuming that this data has been generated from a process that is the following. So the yi is drawn from a likelihood, P of y, given the projection of x along one direction. I'm going to assume that this direction has been drawn from a certain prior distribution. So, okay, I'm going to change notation, I think, slightly with respect to yesterday. So I'm going to put the likelihood to be P star, and then the prior to be P of theta. So that's a distribution over Rd. And this is going to be a likelihood over y. And very importantly, I'm going to assume that xi has been sampled IID from a Gaussian distribution with some covariance and zero mean. And this covariance is going to be a positive definite covariance. So we could do positive semi-definite, but this would be just like, you know, restarting the problem by removing the zeros and focusing on the dimensions which are not zero. So let's just assume that is positive definite. Okay, and so we are going to be studying this problem. Given this data, we want to recover theta star, and the type of problem that we are going to, like, the type of like method that we're going to be using to recover theta star can belong to these two classes. Either we are doing inference or learning. But what I argued last time is that both classes of problems can be encoded in one high-dimensional probability distribution, which is a distribution defined over the parameters, which is what I'm trying to recover. Okay, so these guys, if you were doing something more complicated, like, you know, a neural network, would be a distribution over the weights of the network. Here is a distribution over the weights of this generalized linear estimation problem. And okay, so this distribution, I'm going to be using the fact that it's IID over the samples. So I'm going to write this is a product from 1 to n of some likelihood that I'm using for inference of yi given theta xi. And then I have a prior, which I call phi of theta. And finally, I have a normalization. Okay. So the very important point that I tried to make last time is that this likelihood and this prior might not be the likelihood and the prior that generated the data. Okay? It can be, but it can be more general than that. They don't even need to be proper distributions. They can be like just pseudo distributions. So like they don't need to be normalized, for instance. So one example, which is the case of base optimal inference, is when psi equals to p star and phi equals to theta. That case, we are doing just base optimal inference, and we know that estimators that can be derived from this distribution, they are optimal in some norm. That is, depends on the norm that you choose. You can derive optimal estimators by sampling and building statistics out of that. So for example, the minimum mean square error is just the posterior mean. It's just the mean of this distribution when this guy equals to this guy and this guy equals to this guy. That's not true in general. So if these things are not the same, then the mean square error of the mean of that might not be optimal. Another case that we introduce is the case where this likelihood corresponds to a loss function, and this prior corresponds to a regularization. And then we saw that, if we take beta, the factor in front of the loss function, the regularization to infinity, this distribution is going to be picked on the minimizers of the empirical risk minimization problem associated with this likelihood and this prior. And so we can also study ERM by studying that. Okay. Do I want to say something else about it? No. Okay. And third thing, and very importantly, about the setting, it's good, is that we are going to be studying this problem in this high dimensional limit that Cynthia introduced like in her lecture last time. So we are going to be working in the high D limit, which is the limit where n and d go to infinity at a fixed ratio n over d converging to alpha. Alpha is a number, is a theta 1 quantity. Okay? So we argue that in this limit, we're going to be able to say interesting stuff, which is not captured by classical statistics when just you take n to go to infinity and d is fixed. And okay, that's something that you saw yesterday, so I'm not going to motivate anymore that because I think like Cynthia has been very convincing already that that's an interesting limit to study. One thing I should say though is that whenever you are studying asymptotics, you need to be careful about the order of magnitude of the different quantities involved in the problem. So since you're taking these guys to diverge, like for example, our covariance is a d by d matrix and d is large, so this covariance is growing. So I need to make sense of like a limit for this covariance. So what I'm going to assume here, maybe I can put here as a 4. Let me put in the same, but let me put it aside. We are going to assume that the norm of theta star, which essentially is the variance of this prior, this is going to be a theta d quantity. And we are going to assume that the trace of sigma is going to be a theta d quantity as well, okay? So for example, if theta is the identity, that's just d, so good. But sigma can be anything, and you can think like one way of it, like of having this limit well defined is that you can think like, let's say that sigma has a well-defined asymptotic spectral density. So if I take the eigenvalues of sigma and I define the empirical eigenvalue distribution, this empirical eigenvalue distribution converges towards something which is like a good distribution. So, and okay, and we are assuming that the variance of theta star is also of order d, and this is going to be important because you notice that I put a D here. So the norm of X is of order 1, which means that the elements of X are kind of 1 over square root of D. And so this scalar product is of order 1, okay? Because this is of order, like elements of these, like this is of norm of order D, and this is of norm of order 1. So when you take the sum in the scalar product, this is like a random variable which has order 1. So this scaling is in order to make this thing a order 1 quantity in the limit. However, I'll make a comment later on that even though we are making this assumption, and even though we are going to work in this proportional asymptotics limit, some of the results, in some cases, are quite close to non-asymptotic results you can derive. So if you are familiar, just that's kind of a spoiler, but if you are familiar with non-asymptotic, for example, upper and lower bound for linear regression, like, you know, there is this very well-known paper by Ziegler and Bartlett on benign overfitting of linear regression, where they derive upper and lower bounds for linear regression. And if you compare these upper and lower bounds with the exact asymptotics in the proportional regime, it's pretty much the same up to some constant that goes to 1 when d goes to infinity. Okay, so I'm gonna come back to this. It's not always true. For some problems, this proportional asymptotics is not the full story. For some problems, it can be the full story. Like we can capture both the extreme when you take like alpha to infinity or alpha to 0. They're well captured by the proportional asymptotics. Okay, we're gonna come back to this next time. Okay, so given that, we want to study this measure and want to derive a large deviation principle for this measure. So as I motivated in the second lecture, is equivalent to study a large deviation principle for, like, let's say this, and to study like the free energy density. So let me define. So define the free energy density. Of the log of the partition function. And note that the partition function is a function of the data. So it's a function of D. I didn't define D, but yeah, where D is just like the pairs of xi, yi. So the partition function is a function of the data. And this already shows that there is a one key difference with respect to the Curry-Weiss model that we studied last time. So in the Curry-Weiss model, the partition function was a function just like of a few parameters like the temperature, the external field, and so on. But now we are dealing with an object which is considerably more complicated because the partition function is a function of some random quantities, some quantities that have been sampled from this data generating process. That's in physics what we call quench disorder, and means that, you know, the Boltzmann-Gibbs distribution associated with this problem is itself a random measure because it depends on x and y. So now we are not only studying like the high dimensional limit of a probability distribution, we are studying the high dimensional limit of a random probability distribution. So in general, and that's something that requires a bit of justification, but here I'm gonna be basically like not going too much into that because it's a bit technical, but in general, for the problems that we're gonna be interested to study, this quantity concentrates in the limit. So studying this quantity or studying the expectation of this quantity and the expectation in respect to the randomness, which is the data, it's the same thing. So you can prove concentration for that. Sometimes it doesn't concentrate, so you need to be careful. But, you know, in the case that we're going to be studying, they concentrate. So it's going to be equivalent to study log ZD or expectation of log ZD. So if you are interested about like details of that, like come to me and we can chat later. Okay. And by the way, when I write this limit, I actually should be writing like something like this, just to stress that is the proportional asymptotics. But typically, I'm just going to write lim of d going to infinity, and implicitly it's under like assumption 3. Okay. Right. Now, yeah. No. Sorry, that's alpha. This is alpha, not infinity. Very important, because if n over d goes to infinity, then we are back into classical statistics, and we have very good guarantees for that. So let me take the opportunity of your question, like to remember that, like if we are doing for example maximum likelihood when n goes to infinity and d is fixed, so we have very good guarantees. We know that the estimator has Gaussian statistics. We can build confidence intervals. We are very happy. If you're doing based optimal inference, we have also like Bernstein von Mises theorem. It tells you that everything that you hope to have for your estimator, you have it. Now the real challenge here is actually that we are not n over d going to infinity. We are n over d is a constant, and that's going to capture as Cynthia was telling us yesterday. For example, you can prove that like the estimator that you get from maximum likelihood in this case actually is biased. So it's like you're not even getting an unbiased estimator. Confidence intervals are overconfident. Like there are all sorts of consequences for statistics if you are interested. So I'm not going to go too much in detail, but I mean I have some work on uncertainty quantification in this regime, and there are a lot of bad things that can happen, and you need to fix it in this case. And by the way, all of these bad things that happen will depend on the data generative process. Different from maximum likelihood estimation, right? So when you do maximum likelihood, you essentially assume that you are well specified and you have all your guarantees, and essentially kind of agnostic from the data distribution. While here, all the results that you're going to derive are strongly dependent on the structure of the data, and that's, I tried to argue last time, that's both interesting and challenging, because becomes a big business to find good models of structured data that you can actually do the calculation that I'm going to do now. So a lot of work has been spent over the past few years, like trying to understand what are good structured models that we can actually solve. Okay, so now I'm going to essentially embark into a like very long and tedious, I guess, for some people, calculation. So I'm just apologizing beforehand, like there is no way out. Like I could have like kind of tricked you into a simpler path to solve this problem in a specific setting, but okay, again, I want to give you methodology. So I'm gonna do the actual full thing, and I'm gonna try to make it as digestible as possible, but there is no way out. Like it's a complicated computation, so if you want to learn about this method, that's the only way to do it. So yeah, so bear with me, and then next lecture, we are going to draw the consequences of what we derive. But keep in mind that our goal, in the end of the day, it's very easy to lose sight of the goal once we are in the calculation mess. Our goal is that we want to derive something like this limit, minus f asymptotically is characterized by, let's say, the minimum or the maximum, like in this case, the maximum is minus f of some parameter that lives in some subset of R. Let me put it this way. Or it can also be like, it can also be a couple of parameters. So let's say Rk of some rate function. That's what we want. Because once we have this, we can essentially completely understand all problems of all the statistics of this problem. And there are going to be two main, let's say, challenges. So one is actually dealing with this object, this high dimensional probability distribution, and the other one is kind of finding what are the good summary statistics that are going to be describing this limit. Because in general, if I give you this problem, it's not so obvious if you didn't see it already. What are the good, like, low dimensional quantities that describes the statistics of the distribution. Like what is the equivalent of the magnetization for this problem, right? Finding these order parameters is never easy. Sometimes it is, sometimes it is not, and it's part of the challenges to find this thing. Okay, so let's go. So there are 6 steps in the computation. So fasten your seatbelts, and step number 1. So step number 1 is perhaps like the most important step. If you haven't seen this before, is what I call the replica trick. By the way, we are using this to study this class of problems, but the same method can be used. I know some of you are working on optimization problems on graphs or constraint satisfaction problems. Some of you like come from information theory, like and studying the capacity of some channel, and this method can be used for also this problem. So with slight adaptation, but it's a quite general and powerful technique. Okay, so the key idea is that the challenge of doing this is that you need to compute the expectation over a high dimensional distribution. So the data distribution is high dimension of the logarithm of something which is also high dimensional integral, right? Because this is the integral over, this is a normalization. So that's the integral over mu. So you have 2 high dimensional integrals to make. And in the middle, there is a log. So that's bad. So the first step is like to get rid of the log. And the replica trick just tells us that, if you want to study the log of z, you can write this as the limit as s goes to 0 of the derivative respect to s of moments of z. So if I know how to compute moments of z, all moments of z, I can just get the log by taking the limit of the derivative of the moments. So that's the first important step. And this implies, in particular, therefore, minus f can be written as just the limit as d goes to infinity of 1 over d of the limit s goes to 0 of the derivative of the expectation of z, the power s. And again, the expectation is over the data. Maybe this s should be here. Okay, so this reduces our problem to the problem of computing moments. So that's what we're going to do. We're going to compute moments. So step number 2, I'm going to switch here. So step number 2 is the computation of moments. So, well, if s is integer, and here is the catch, because that's exactly like the biggest difficulty of making whatever I'm going to do here rigorous is this loop that I'm going to make between integer moments and continuous moments. Because for the limit, I need actually to understand this for any real s, right? But what I'm going to do here is that I'm going to compute for integer s, and I'm going to do some continuation argument. But let's do what we know how to do, which is like, let's just write like what is z power s to the d. So that's just, I'm going to go slow in the beginning and then accelerate as we go. So that's this. That's an integral over rd of the power s. So what is this? This is, I can introduce a letter a that actually is the product of the integral over d theta a phi theta a of the product okay. Good. Now I just need to take the expectation. So let's take the expectation on both sides. So I can take the expectation respect to D. Maybe before just to, yeah, no, let's take the expectation. So now I need to take the expectation respect to the data distribution. The data distribution is this. So what is that? Well, I can write this expectation as, okay, the expectation of that, just put on both sides. And I can already simplify in this way. I can already rewrite in a d theta star of p of theta theta. So that's the expectation over the target weights. And then I have one integral a from 1 to s d theta a phi theta a. And then I have everything that depends on the likelihood. So I have the likelihood of the data and the likelihood of the model. Both are IID, so I can just pull this product out and write this as the integral over dy I of the expectation over x I. And then here I need to put the likelihood. So I have the likelihood of y I given theta star xi. And then I have the product over A from 1 to S psi of yi theta A xi and close brackets. Okay, so all of this is the integral. Okay. By the way, correct me if I write something wrong on the board, because often the mistakes. Yeah. Okay, so that's a good question. Is that yes, you need some assumptions, but I'm not going to go over that because of the following reason. So the method I'm going to use is not a rigorous method. It's going to be heuristics, and for the purpose of the method, I don't need any of these assumptions. So adding just one layer of heuristics on the top of heuristics is still give me heuristics, so I'm not going to worry about that. But but that's a good question because whenever you want to prove this result, so I should mention this as well, is that everything that I'm going to be telling you for these models, for this class of models, if I'm not mistaken, I think everything is rigorous, can be made rigorous. And then when you make it rigorous, you need to have the assumptions over the likelihoods, over the priors, and etc. And the assumptions will depend on the problem, because that's one very interesting thing about the replica method is that you cannot prove the replica method, or at least we don't know how to prove the replica method. We know how to prove what we get from the replica method, which is the rate function, the variational problem for the rate function. So this is something we can prove. So for certain likelihoods and for certain priors, let's say compressive sensing, where the prior is sparse, and when the likelihood is just the linear model, just the Gaussian likelihood, we know how to prove this using some techniques from high dimensional probability. For other problems like ridge regression, we know how to prove this with random matrix theory. So with random matrix theory, the assumptions that we need, for example, on X are quite mild, like just like existence of some moments. While if you want to prove the same thing for logistic regression, is much more complicated. So maybe we need some stronger assumptions like sub-Gaussianity and so on. So proving each of these variational principles is going to require different assumptions. So that's why for now I'm not going to go into that. But yes, in practice, if you want to make these results rigorous, you need some assumptions on the distributions. Yeah, so that's if you can think as a matrix, if you want. So it's essentially like copies. So if you want, okay, maybe I can put this as a side. Yeah, so note, you can think as a phi of theta of A, yeah, just as equals to phi of theta 1, theta 2, theta s if you want. And when I have product, for example, the product over, let's say, A from 1 to S of d theta A is really the measure over, d theta 1, d theta 2, d theta S, and so on. So of course, like these are independent copies. So actually, this is equivalent. Maybe I should not have written this. Exactly. Yeah. Exactly. Yeah. Oh yeah. Sorry. Maybe I should have understood the question this way. Yeah. It's just a superscript. But you can think about it as a matrix as well, right? Because you can think about this integration as now being an integration. Where is it? This integration is being an integration over S cross D. Because you are doing like a huge integral, like S integrals in RD. Yeah, these are independent copies, so yeah. Yes. Yeah, I didn't do anything. I didn't do any. I mean, I'm gonna, since I know the audience is not like is not familiar with that, and moreover, the audience is like majority of people from CS or maths. I'm gonna try to make sure to stress what are the, let's say, wizardry tricks, like. But this is just like, yeah, this is kosher, like. Step one is problematic, yeah. But okay, no. Step one is actually fine. This is rigorous. Like now, step two is also rigorous, but the problem is like when I actually need to take the limit inside these integer moments. But so far I didn't do anything. I didn't do anything weird. Okay, so now that we did this, um, what do we need to do? Like we need to actually to compute the expectation, right? So the expectation over x is a Gaussian variable. And now x appears here in these likelihoods. So essentially, I can write, so note, that I can define these variables like new I equals to theta star xi. And I can define this lambda a as theta a xi. So these are real numbers. And these are jointly Gaussian variables conditionally on the weight. So condition on theta and theta star, they are jointly Gaussian. Right, so I can actually just compute what is the distribution. I need to compute the mean. So the mean is 0 conditionally on the weights. That's easy. And then I just need to compute the covariance. And what is the covariance? Well, I can compute that, x of nu lambda a, and all of these things have indices I. That's just simply what? So that's just simply 1 over d theta star sigma theta a. So I just need to compute the expectation over the scalar product. And now if I do I, A and B, this is 1 over d theta a sigma theta b. And similar, the expected value of nu squared is just 1 over d, the norm of theta star respect to sigma. Okay. And here you can see already like where my definition, like where my assumptions go, like is I want to make sure that these quantities are order one quantities in the limit. Like they are numbers. They are numbers that are going to concentrate. So I have like, I need these quadratic forms to concentrate in the d going to infinity limit. That's why I need these assumptions on on the norms and on the trace of sigma. Okay, so good. Yeah, I'll have to erase because I don't have a lot of space. So okay, so once I realize this, I can essentially like let me define these quantities to be, you know, this guy I'm gonna call it rho. So this guy I'm gonna call it QAB, and this guy I'm gonna call it MA. So I'm just giving names to these quantities, and these guys are gonna be my summary statistics. These guys are the guys that are gonna appear in my rate function. These are the, let's say, low dimensional quantities that parameterize the full statistics of the problem. And now it's quite intuitive in hindsight, right? Because what are these guys? So this one is the correlation between the target weights and the weights that I'm estimating in the space of the covariance, so weighted by the covariance. So this guy is the correlation between two samples of the weights. So this is a little bit less intuitive, I would say, but you can think about it like, you know, since we're studying like these Boltzmann-Gibbs distributions, like I take two samples of the independent samples from the Boltzmann-Gibbs distribution and compute the correlation. So this is kind of parameterizing the norm and the variance of the Boltzmann-Gibbs. And this guy is just the norm of my target function in the space of the covariance. So these are just like correlation functions. So it's kind of intuitive that you just need to track correlation functions because the data is Gaussian. So since the data is Gaussian, essentially just like second moments, first and second moments matter. So it's kind of intuitive that you just need to track these things. In hindsight, it's kind of intuitive. Okay, so now I need to compute the expectation over x becomes an expectation over nu and over lambda a. So what I'm going to do is then I'm going to try now to do this expectation. Okay, so if you want, I can call this whole thing star. And then star equals this. So that's an expectation over P star of Y. So everything has an index I, but it doesn't matter because everything is IID on I. A of P also psi I. Okay, so that's good. That's good because I now got rid of the expectation over x, and now I just have expectation over low dimensional quantities, right? Like I started with this expectation over a variable in RD. I realized that the expectation in RD actually in disguise is just an expectation over what? There's S variables here and plus one, so S plus one variables. So S I'm gonna send to 0. So this is low dimensional, while this was high dimensional. So that's I'm in business. So let me just introduce some notation so that I don't have to write this whole thing over and over. Let me call this guy so psi. Oh, psi. Okay, what's the? Yeah. So sorry, I want psi to be something else. Okay. So I have this. Now let me go back to the original thing. So I can write. I'm going to define psi of so that's like it's a uppercase psi of y s that depends on rho ma in QAB, and that's going to be the integral over y of this expectation of star of the expectation of mu I, no more I, lambda A of all this thing here. Okay, so I'm defining this, and so that in the end my expectation over z to the power s simply can be written as d theta star p theta theta star integral over a d theta a phi of theta a of psi s y to the power psi y s to the power n. Okay, are we good? Any questions about that? Did I try to be like as step by step as possible? So what I have achieved is that I started with computation of a high dimensional integral over x. I use the fact that they are Gaussian, like the conditionally on the weights, the projections are Gaussian, because everything only depends on the projections. The projections are Gaussian, then I can rewrite this integral as an integral over the moments of this Gaussian. And then in the end of the day, I just have like now integrals over theta of this potential function. And this potential function, let me put myself a bit ahead, is the energy function, right? It's exactly like the likelihood of the problem, the two likelihoods of the data and of my model. These are going to be like setting the energy of the problem later on. Of course, this potential depends on theta and theta star. So I didn't manage to factorize the distribution because these guys depend on these moments, and the moments depend on theta star and theta. So this is still like the same integral as before. It's just that now I'm writing everything is just a function of the moments. Yeah. Yeah. Yeah, because essentially I have these integrals over theta here. So everything that is here is kind of, I can think as conditionally on theta. But of course, then I need to integrate over theta. Yeah. Yeah. No, actually, it's a power. And why this is the case? Maybe actually I could have done one more step. Is the fact that here you have this product. So I could have written this as just a power over n because everything is id over I if you want. So the index I is always I, and I have a product over I of the integral. So all of these things. So I'm gonna do something that is not very nice to do in the board, but if you're taking notes, but I could do this if I wanted. And I should have done probably to make it clear. And then erase all indices. You should have done this before taking the expectation. Okay. Okay. So far, we didn't do much. By the way, this computation is kind of strange the first time you see, because first it looks like you're doing nothing, and then at some point it looks like you're complicating the problem. You're gonna see it's gonna look like I'm making the problem harder, and then at some point everything is gonna collapse into something simpler, and then you're like, wow, what just happened? But okay, just a spoiler. Okay, that's step 2. Great, we took the average over the randomness, and now we have something that just depends on the moments. Step 3. Step 3 is entropy versus energy decomposition. remember in the Curry-Weiss model that once I realized that everything depends only on the magnetization, I wrote my Boltzmann-Gibbs distribution as a probability distribution over the magnetization. And the price I paid to go from the original distribution to this new one is that I need to add this counting factor, this factor that counts how many configurations have this magnetization. And that eventually led me to the entropy factor that appears in my large deviation principle. That's exactly going to be the same here. I wrote now my partition function only as a function of the moments. And now I need to count how many configurations of theta have a fixed correlation M, rho, and QAB. So that's what I'm gonna do now. So, okay. I'm gonna introduce variables M, Q, and rho, and I'm gonna try to decouple the dependency on theta from the energy term. So this guy is the energy term, and I'm gonna try to make the energy term depends on theta because the correlations depend on theta. I'm gonna try to make the correlations independent of theta by introducing the constraint explicitly. So essentially, I'm gonna use over and over the fact that that I can write. So I use P of y, just the things that everybody know. Like if you have something like y is a function of x and both are random variables, then you can just write this, right? If you have like y equals to f of x and both of them are random variables, then you can write distribution of y by introducing the delta functions. So I'm going to apply these, apply to the overlaps or correlations. So, for example, MA equals to theta A sigma theta star over D. So let me give you an example. I'm just going to write, I'm just going to write like identities over and over, or same for UAB and for rho. So let me write the following. Expectation over Z to the power S. I'm going to write as an integral over rho, an integral over M, and an integral over Q of two terms. There's going to be my original term, and then I'll have to introduce this new term. So yeah. Right. So I'm going to rewrite this way where Vs is just going to be, the expectation over theta star, the expectation over all theta I, so theta from 1 to S, which essentially is this part of the constraint. So delta of rho minus 1 over D theta star sigma theta star. Then I have what? I have times a delta MA minus theta A sigma theta star 1 over D. And then I have AB delta of QAB minus 1 over D theta A sigma theta B. Okay, so I'm now trying to exactly introduce this entropy term that is counting how many configurations there are with a given overlap of a given correlation function. And the way to do it, like one way which is a bit, in the curvized model was easy because it's just like, counting things in binary variables. Here is a bit more complicated because these are continuous variables in principle. So one way of counting this volume is just to define this expectation over the weights of the constraint that fixes that the correlations are given by that. So you can see this as kind of a volume, like the volume of configurations that have that correlation function. That's exact. So far I didn't do anything strange. But you can see why it seems that I'm complicating the problem, because here I have these integrals and I'm introducing new integrals. So now I have here one integral, s integrals, s minus 1 over 2, because these guys are symmetric. So integrals, so I have now a lot of integrals over s. And I still have my original integrals over the weights. But now, use the fact that I can write the Fourier representation of delta use this to express these delta functions now in Fourier space. And why do I want to do that? So the reason why I want to do that is that all of these things are kind of scalar products. So if I exponentiate these things, I can pull out the sum that defines the scalar product, because the scalar product is just like, sum over I, xi, yi, and I want to pull out this sum over I. So going to Fourier space allows me to factorize this sum. So for example, you can write, I'm going to write only one. You can write d ma of delta of ma minus 1 over d theta a sigma theta star. You can write this as the integral over a dma hat, that's my Fourier conjugate, over 2 pi exponential of minus I ma and the sum over a m hat a ma minus 1 over d theta a sigma theta star. So just do that for every single delta function, okay? For QAB, and so on. And this implies that this entropy potential can be rewritten as follows. So it's proportional to integral over d rho hat over 2 pi integral over a d. Oh yeah, sorry. I should just write because the way I define the integrals over dm and q are outside. So let me start again. M hat a 2 pi ab dq hat ab 2 pi, and then I get just like a bunch of exponentials. So actually I forgot to write my expectation over theta star and all theta a. So now this is just like, abusing of notations, theta 1, theta 2 up to theta s, and a bunch of exponentials. So I have minus I rho hat rho plus actually yeah, minus 1 over d theta star sigma theta star plus sum over a I m hat theta a sigma theta star, and then times e minus I sum ab q hat ab times qab minus 1 over d theta a sigma theta b. Expectation. Okay. See what we got. So finally, if I put everything together, I can now write the following. I can write the putting together I can write the expected value over d of zs equals to integral over d rho hat. And actually, this is not equality, but it's proportional. So I'm not caring about the constant factors because anyway, I'm going to take the log and the derivative. So constant factors in front of this will not matter. So allow me just to not care about them. dm hat a integral ab dq ab. So these are all the integrals that I have times exponential. And then I'm going to note that I can pull out this factor d. So, you know, all of these things have a factor d here. So I can actually like just changing variables like on q to make the factor d to appear here, like either I divide by 1 over d here or here. Equivalently, I could have introduced the constraint d times rho, and this would just give me a constant. D times a big potential S that depends on rho hat m hat qab hat. And if you want, I can write to you this big potential. It is equals to, there is minus rho hat minus sum over a ma hat minus sum over ab qab q hat ab. So these guys come just from this part here, right? So this is just like the part of the Lagrange multiplier that I introduced that are proportional to the Fourier coefficient times the correlations. And then now I have my entropy and my energy. So I have plus alpha times the energy potential. So the energy potential, I didn't do anything. It's just there as it was. And remember, the energy potential is only a function of rho, only a function of the moments. It doesn't depend on the hats, because the hats are introduced through the entropy. And then I have plus this entropy potential, which only depends on the hats. Where alpha, remember that alpha is equals to n over d. And this is going to come from this n when I exponentiate this thing. And let me write to you explicitly, for instance, like, let me write this guy here. So let me write one of them. For example, the energy one, that's going to be just the log of dy d nu e star y given u integral over a d lambda a on p of y given lambda a times the Gaussian measure with for nu and lambda a, and with zero mean and covariance given by rho, MA, MA, and QAB. So you see that the exponential of, so d times alpha produces n. So you have n times log. So the exponential of n times log is the whatever is inside the log power n, and whatever inside the log is exactly what I had here. So okay, maybe I should not have called the same letter. Let me just for make these different. Let me call this phi of y. Let me call this phi of theta. So essentially, phi of y is just the alpha times the logarithm of this one. And similarly, we can write this one as just like exponentiating all these guys up to the factor of the constraint here that I put outside. So let me maybe write this explicitly so that you don't feel that I'm tricking you by hiding things. Let's write phi s theta. So this is just equals to 1 over d log of the expected value over theta star, theta 1, theta s of E of I rho hat theta star sigma theta star times E of I sum m hat A of theta A sigma theta star times E I AB Q hat AB theta A sigma theta B. Okay, so exponentiate this, you're going to see that this gives exactly V. Yeah. Yeah, there is I. Yeah. So yeah, if you want, okay, so that's a good point. You should have I's all over here. Now, what I can do is that I can change variables on this integral since I'm integrating over these things. So I can put the I's inside the integral, so I can get rid of them here, and I can get of them here. So that I essentially change variables like m hat goes to I, or I m hat goes to m hat, I rho hat goes to rho, and I QAB goes to QAB. And now I need to integrate over like the complex axis. Yeah. So yeah, so I'm not writing here like the domain of integration, but now I'm integrating with the complex plane. But this will not matter. And I'm now going to explain why this is not going to matter. But because in the end of the day, so if you think about the co-revised model, a key step of the co-revised model is that when d is large, the exponential over d times the potential, like the integral over the configurations of the exponential of E times the potential by the Laplace method satisfies this large deviation principle. So the same thing is going to happen here, because if you notice, the reason why I want to write things this way, there's a d here. And so when d is large, this integral is going to be dominated by the configurations that extremize this potential. I can extremize, I never need to do the integrals actually, because I just need actually to solve the extremum over that, over these 6 variables. And that's where we are going now. Any questions about that? That's exactly the moment where things seems to be getting crazier, because now I have like all these integrals over q, m, and rho, and it seems hopeless to do actually this integral. So why do I actually introduce these integrals to start with? Initially, I had just some high dimensional integral that I still have this high dimensional integral over theta star and theta a. But now I have many more integrals over this space of replicas. That is the space that I just introduced by hand. So what I'm doing here. Okay, everybody's good so far? So that's step number 3. So now let's consider step number 4. And step number 4 is one of the crucial steps, because once I have achieved this, to write the moments as an integral over some low dimensional quantity, some summary statistics, and this integral takes the form of an exponential with d, which I'm going to take to be large, times a potential, and this potential is order 1 by all the assumptions that I made, then I can just apply Laplace method to this integral. So, or since I'm in the complex plane, the saddle point method. So, saddle point. And that's the first time I'm actually taking a limit. So far, I didn't take any limit. Everything is exact. Actually, all of that is exact. Like, I didn't do anything strange so far, and I'm going to take a limit. Saddle point method, which tells me that actually this expected z to the power s asymptotically, when d n go to infinity, and very importantly, this stays fixed, because notice that I crucially have an alpha here. This thing is going to be dominated by the exponential over d times this potential over the values of this potential that extremize it. So now I traded these integrals over the summary statistics for an extremization problem. So where I need to solve the problem of extremum of phi s of rho ma qab hat. And I need to extremize over all these variables. Okay, so here essentially I already have my large deviation principle, right? I managed to write the free energy density in the high dimensional limit as an extremum over the potential. The potential is over quantities which are low dimensional. So these are matrices S by S and a vector of dimension S and just a scalar. S is supposed to be small because I need to take this S going to 0 limit. But these are like quantities which are not divergent in the dimension. They are quantities that actually stay like real numbers with the dimension. So essentially here, I'm essentially done with the large deviation principle. But I'm not done with the computation because now I need to solve this extremization problem. And it's just hopeless, right? Because I need to extremize over matrices of size S by S, which S is going to 0. Like what this even means, right? So I'm still not happy because I cannot do this. I cannot do this. And when I say I do this or not, like ideally I want something that I want to plug in the computer and I can do in the computer in, less than half an hour. So I cannot do this in the computer in less than half an hour, right? I mean, I don't even know how to tell the computer how to take S to 0. Like, so I'm not that happy. So any questions about that so far? Because the next steps are going to be about simplifying this large deviation principle that we derived for the free energy. So note that this is exactly the free energy. This is going to be exactly the free energy because then I just take the log and then I divide by d. So this is exactly the value of this potential at the extremum is exactly the free energy density. Just like for the Curry Weiss, the value of the potential at the extremum was the free energy density of the Curry Weiss. Objections like confusions. So far, so far everything that I did, I mean, there is nothing wild about anything that I did. So all these steps, like step 1 is justified. Then step 2 up to here, if I treat S as an integer, everything is fine. I'm not being careful because I should be doing the saddle point method on the complex plane because I change variables to be in the complex plane, so I need to be careful. So I'm not writing whether this is a minimum or a maximum because whether it's a minimum or as a maximum depends on this integration that I do in the complex plane. So I'm not being careful about these things. But you could be careful about these things, and you could completely make this fully like rigorous up to this. Of course, like as Siva is already hinting, the problem is going to be from the moment where I actually want to take S to 0. And that's going to be, let's say, the leap of faith. Okay, step 5, replica symmetry. So for me, a replica is a sample from this Boltzmann-Gibbs distribution. So I take 5, I have 5 replicas. So since here I need to take S, so if you notice, like the first step that we did was the partition function to the power S. And this is essentially writing like S integrals over samples over the posterior. And this posterior, then I use Bayes' rule to be able to write as the likelihood and the prior. But essentially what I'm doing is that taking this integral to the power S is like sampling S configurations from the posterior distribution. And this is what I call the replicas. And yeah, the reason we call replica trick is because we write this log as the expectation over a replicated system. By the way, I should also mention here something interesting is that that's actually a pattern in all these problems in spin glasses and disordered systems. Is that notice that when I introduced my replicas, they were independent, right? A was like an index that was just multiplying. There was a product over A of an integral, right? And then I took the average over the randomness over X. As soon as I took the randomness over X, I introduced coupling between replicas because now I have integrals, where it is. I have integrals over AB. that I didn't have before, right? I just had integrals over A. So the system had independent replicas and it was random. And once I get rid of the randomness, I have interactions between the replicas. So this is always a pattern in disordered systems. When you have a system which has quench disorder and you take the average over quench disorder, you can write this as an effective problem where the replicas of the system are interacting here through this, through this potential. Now we have an energy for the summary statistics, and in the space of this summary statistics is an interacting problem. You have actually replicas interact with this two-body term QAB. And that's going to be the case for essentially all models that I know from disordered systems. Once you take the expectation of the disorder, you couple the replicas. You can see the replicas as realizations, like realizations of the posterior distribution, independent realizations. And then you're trading the disorder by coupling this. So you're tracking correlations of the posterior. So makes sense that you have this trade-off. Okay, so now it comes like one of the, let's say the crucial, so let me just make a little stop here, because we are almost out of time. But let me make a comment about this. What is going to happen now? So we derived the large deviation principle. However, the large deviation principle is hopeless because although is of the form that we like, extreme over a potential over some summary statistics, we now, to be able to get the free energy density, we need to take the limit of S going to 0. Actually, I need to take the derivative and then S going to 0. But first, I need to extremize over the variables. And the variables are matrices and vectors, which are of dimension S. So if I knew how to extremize this, then I could take the derivative, and then I could take the limit, and then I'm in business. But of course, extremizing in the space of symmetric matrices is going to be as hard as the initial problem of sampling from the high dimensional distribution. So it's hopeless to actually attempt to solve this large deviation principle. So what we want to do is that we want to do something like we want to simplify this. And typically what we do when we want to solve some complicated problem like that is that we make an ansatz. We say, okay, let's say that instead of minimizing or extremizing over this full space, let's look at a slice that is particularly simple to extremize. Let's extremize on this subspace, and let's hope that the solution in this subspace is the good solution, right? That's, for example, what we did also in the variational principle. So that's a thing that we always do when we have a problem which is too complicated. We try to impose a family of subsets which we can solve, and then we hope that this is good enough. And here it comes, let's say, the physical intuition of the problem, because the ansatz that you're going to make on these variables are going to translate your belief of how the Boltzmann-Gibbs distribution is behaving, right? How this high-dimensional probability distribution factorizes, for example. It's just going to factorize like in a naive mean-field way, like it was for the Curry-Weiss model. It's going to be more complicated. So essentially imposing an ansatz here is imposing some belief of how we believe this distribution behaves in high dimension. And finding a good ansatz, it was a big challenge in physics for many, many, many years. So essentially, the history of spin glasses is that like the SK model was introduced, people started like making this type of computations very early when it was introduced, because this type of methods were already let's say common knowledge in physics. And however, when they got to this point, it was not very clear what kind of simplification you should make. And the first people that arrived there, they proposed simple simplifications, and they were obtaining results which were completely off. And they were like, okay, we don't know what is a good variational family here to actually solve the problem. And that was until Giorgio Parisi came. And so what Giorgio Parisi did, let's say one of his biggest contributions here, is that he gave a systematic recipe to create ansatz for this potential. So he said, okay, you try this family, and if it doesn't work, you go one family higher, and there is a recipe to find this. It's not like something that you need to guess. It's like, then you do that. And if this doesn't work, you do that, and so on. And you move in a hierarchy up to a level where you treat the full problem. And these are what is called like, the Parisi ansatz. And, how he got there is a very interesting story. Like, I recommend that there are like several like testimonies and books and stuff like, but essentially this was the genius step. Like, is to find this family of ansatz to solve this problem. And here, what you're going to do next time and finish this computation is that we're going to see the first step of this recipe, which is called the replica symmetric ansatz. And we know, because we can prove that the replica symmetric ansatz is exact for two classes of problems. So one class of problem is base optimal inference. So whenever your posterior distribution is well specified, so your likelihood is the good likelihood and your prior is the good prior, then the problem is replica symmetric. So what you're going to do here is going to be exact. The second class of problems that this is exact is when the measure is log concave. So in this case, for instance, one specific case of families is like empirical risk minimization with convex loss functions. So if I'm doing ridge regression, if I'm doing logistic regression, like Uber laws, all of these problems, replica symmetry is going to be exact. And that's quite intuitive, right? Because since they are convex, like the measure is like very simple. So like the first step in this hierarchy should work. If you actually take a two-layer neural network and you define the Boltzmann-Gibbs distribution, you're trying to do ERM there, it might not be true because the problem is not convex. So it might not be replica symmetric. And then you have to go one step further. But, the goal here is to do the simplest thing. And then if you like this kind of stuff, you can go and dig. And we can chat, and then you can go and dig for the higher levels of the hierarchy, which are called replica symmetry breaking. And problems like in constraint optimization problems, such as like graph coloring, can have replica symmetry breaking. So then things become a little bit more complicated, and then you need to go down in the recipe that Parisi taught us how to do. Okay, I guess I'm on time, so let's have coffee break, and next time we finish the computation. Thanks.